We have seen that a simple DC motor can be made using a coil rotating inside the magnetic field of a horseshoe magnet, with a commutator being used to reverse the current flow in the coil every 180 degrees. In this lesson, we will look at the improvements that can be made to this device to produce electric motors for various different uses. We will also look at a phenomenon known as back EMF and see how it affects motor operation. In practical electric motors, several coils are wound on a single rotating core, with all the coils lying at different angles to one another. With this arrangement, the turning force acting on the rotating assembly will be more consistent and efficient. The magnetic field produced by the stationary magnet is known as the field of the motor, and the assembly around which the rotating coils are wrapped is called the armature. The armature has a soft iron core to increase the strength of the magnetic fields of the coils. Rather than using a permanent magnet to produce the field, practical motors use electromagnets. These are made by winding wire coils around soft iron pole pieces. The field strength can be adjusted by controlling the current flow in the field coils. You know from the lesson on generators that the movement of a coil through a magnetic field will induce an electromotive force, or EMF, in the coil. This applies to the armature coils in a motor. Lenz's law states that this EMF will attempt to oppose the change producing it. This induced EMF is known as the back EMF. The back EMF will be proportional to motor speed and the strength of the stationary magnetic field. It will act in opposition to the applied EMF. The EMF being felt by the armature will be the difference between the applied EMF and the back EMF. This is known as the net EMF. As motor speed increases, the back EMF will increase, and this will reduce the current flow through the armature. This leads to a reduction in the strength of the armature's magnetic field, and a reduction in the torque output of the motor. The motor speed will stabilize when the strength of the armature magnetic field is balanced by the load. In order to ensure that there is a good flow of current through the armature, the resistance of the armature windings is kept as low as possible. This, however, means that when the motor is first switched on and there is no rotation, and thus no back EMF, the current flow through the armature will be very high. In order to reduce the starting current and protect the armature windings from damage, some motors have a resistor, known as a slow start resistor, in series with the armature coils. As the motor speeds up and the back EMF builds up, this resistor is taken out of circuit by either a centrifugal or a time switch to apply full current to the armature. We have already said that the stationary field of a DC motor is produced electromagnetically, so that by varying the current flow through the field windings, we can vary the strength of the magnetic field produced. There are three types of DC motor in common use, and they are categorized according to the arrangement of their field windings. The three types are known as series wound, shunt wound, and compound wound. The series wound motor has its field connected in series with the armature. The field coil consists of a few turns of heavy wire, and since the entire armature current flows through it, the field strength varies with the armature current. This means that both the field and the armature have very strong magnetic fields on startup, before the back EMF builds up in the armature. Series wound motors therefore have a very high torque on startup. As the motor speeds up, the back EMF increases, and this reduces the current flow in the armature and the field, so the torque rapidly drops off. Series motors run slowly with heavy loads and very rapidly with light loads. You can see that the speed of a series wound motor changes with the applied load. For this reason, they are not used either when a constant speed condition is needed or where the load is intermittent. If the load is completely removed, the motor can dangerously overspeed and possibly disintegrate. The reason for this is that the current required to rotate the motor with no load is very small, and consequently the series wound field coils produce only a weak magnetic field. This means that no matter how fast the motor turns, it will not generate the amount of back EMF needed to balance the applied EMF. The series wound motor has a high starting torque, and because of this, it should never be started without a load being applied to it. Series wound motors are mainly used on aircraft as engine starter motors. In a shunt wound motor, the field is connected directly across the voltage source, in parallel with the armature, and is therefore independent of variation in load and armature current. The magnetic field produced by it does not vary with motor load or speed. This type of motor should be started without a load applied, or with only a light load, as the field has a high resistance. So it takes a time to build up its magnetic force when the motor is switched on. The motor will accelerate with the back EMF increasing until the net EMF is only just enough to sustain the speed. If the load on the motor is increased, the motor slows down, reducing the back EMF in the armature. The reduced back EMF allows the armature current to increase, producing the increased torque needed to drive the increased load. If the load is decreased, the motor speeds up, increasing the armature back EMF and thereby decreasing the armature current and the torque developed, so the motor slows down again. In a shunt wound motor, the variation of speed from no load to normal or full load is only 10% of the no-load speed. Shunt wound motors are therefore considered constant speed motors. Shunt wound motors are normally used where relatively constant speeds under varying loads are required, and for tasks where it is possible for the motor to start under light or no-load conditions. They may be used to operate fans in the air conditioning system. Compound wound motors have two sets of field windings, one in series and the other in parallel with the armature coils. The compound wound motor combines the characteristics of both the series and the shunt wound motor. It has a high starting torque, but it will not overspeed under light loads, and it will maintain a reasonably constant speed under varying load conditions. Compound wound motors are often used to drive hydraulic pumps. Several types of turbine engine-powered aircraft are equipped with starter systems, which use a starter generator having the dual function of engine starting and of supplying DC power to the aircraft's electrical system. Starter generator units are permanently coupled to their engine via a drive shaft and gear train. The units have both series and shunt field windings. For starting purposes, the unit functions as a compound motor, the shunt field winding being supplied with current via an automatic relay-operated field changeover switch. When the engine is running and the starter motor circuit is isolated from the power supply, the changeover relay is also automatically de-energized, and its contacts connect the shunt field winding to a voltage regulator. The machine therefore functions as a conventional DC generator. The advantage of the starter generator is that one device provides two functions, thereby saving weight. That is the end of the lesson. Here is a summary of the main points. All motors produce a back EMF in the armature. The back EMF will be proportional to the field strength and armature speed. It will oppose the applied EMF. Series wound motors have a very high torque on startup. They run slowly with heavy loads, and if the load is completely removed, the motor can dangerously overspeed and possibly disintegrate. Series wound motors are often used as engine starter motors. Shunt wound motors are considered to be constant speed motors. The compound wound motor combines the characteristics of both the series and the shunt wound motor. It has a high starting torque, but it will not overspeed under light loads, and it will maintain a reasonably constant speed under varying load conditions. Compound wound units are sometimes used on gas turbine-engined aircraft as combined starter generators.